The cosmos has been whispering secrets to us for billions of years, but we've only recently learned how to listen. And what we're hearing now, it's nothing short of revolutionary. The James Webb Space Telescope, humanity's most advanced eye on the universe, has just made a discovery that could rewrite everything we thought we knew about our place in the cosmos. We're talking about a planet, a world so tantalizingly similar to our own, so perfectly positioned in the habitable zone of its star, that scientists are giving it a staggering 99.7% probability of harboring life. Let that sink in for a moment. Not a 50-50 chance. Not even a 70% probability. We're talking about 99.7%. That's the kind of certainty that makes even the most skeptical scientists lose sleep at night. But before we dive into the mind-bending details of this discovery, we need to understand just how monumentally difficult it is to find life beyond Earth. We're not just looking for a needle in a haystack, we're looking for a specific atom in a needle that's hidden somewhere in a haystack the size of the observable universe. The challenges are so immense, so utterly overwhelming, that for decades, many scientists questioned whether we'd ever find definitive proof of extraterrestrial life in our lifetimes. And yet, here we are, standing at the precipice of what could be the single most important discovery in human history. The James Webb Space Telescope isn't just any instrument. This isn't your grandfather's Hubble. Webb represents a quantum leap in our ability to peer into the deepest, darkest corners of space and time. Launched on Christmas Day 2021, after decades of development and countless delays, Webb has already transformed our understanding of the early universe. Captured images of galaxies that formed just a few 100 million years after the Big Bang, and peered into the hearts of stellar nurseries where new stars are being born even as you read these words. But perhaps its most profound capability, the one that's relevant to our story today, is its ability to analyze the atmospheres of distant exoplanets with unprecedented precision. You see, when a planet passes in front of its host star from our perspective, an event astronomers call a transit, some of the star's light filters through the planet's atmosphere before reaching us. And embedded in that light is a treasure trove of information. Different molecules in the atmosphere absorb light at specific wavelengths, creating a unique spectral fingerprint. By analyzing these fingerprints with Webb's incredibly sensitive infrared instruments, scientists can determine exactly what gases are present in that distant world's atmosphere. And certain combinations of gases, what scientists call biosignatures, could only be produced and maintained by living processes. It's like being able to smell what someone's cooking from 1,000 miles away, except in this case, we're detecting the chemical breath of an entire planet from trillions of miles across the void of space. The planet in question orbits a star that's been cataloged as K-Tuan-Gative-18, located approximately 124 light-years away from Earth, in the constellation Leo. Now, 124 light-years might sound like an incomprehensibly vast distance, and it is. If you could somehow travel at the speed of light, it would take you 124 years to get there. In more practical terms, using our current fastest spacecraft, the journey would take roughly 2.3 million years. So, no, we won't be sending a probe there anytime soon, and we certainly won't be establishing a colony in the foreseeable future. But the beautiful thing about modern astronomy is that we don't need to physically go there to unlock the planet's secrets. We can study it right from our cosmic backyard, using the sophisticated instruments we've placed at strategic points in space. K2-18b, as the planet is designated, was actually first discovered back in 2015 by NASA's K2 mission, which was the second phase of the incredibly successful Kepler Space Telescope's planet hunting campaign. But that initial discovery only told us the basics: the planet's size, its orbital period, and its distance from its host star. What scientists really wanted to know was what this world was actually like. Was it a barren rock? A gas giant? An ocean world? And most tantalizing of all, could it possibly support life? For years, K2-18b remained a fascinating mystery, one of thousands of exoplanets cataloged but not deeply studied. But everything changed when the James Webb Space Telescope turned its golden mirrors toward this distant world and began its meticulous analysis. What Webb found has sent shockwaves through the scientific community and captured the imagination of people around the globe who've been wondering for their entire lives whether we're alone in the universe. The planet itself is what scientists classify as a sub-Neptune, meaning it's larger than Earth but smaller than Neptune. Specifically, K218b is about 2.6 times the radius of Earth and roughly 8.6 times its mass. This puts it in a category of planets that we don't actually have in our own solar system worlds, that are too big to be rocky terrestrial planets like Earth, but too small to be ice giants like Neptune or Uranus. For a long time, scientists weren't even sure what these intermediate-sized worlds would look like. Would they be mini Neptunes with thick hydrogen atmospheres? Super Earths with rocky surfaces? Or something entirely different? Webb's observations have started to answer these questions in stunning detail. The spectroscopic analysis revealed something absolutely extraordinary: the presence of methane and carbon dioxide in the planet's atmosphere, which is exactly what you'd expect to find on a world with liquid water oceans. But here's where it gets really interesting, really fast. Webb also detected a molecule that made scientists' jaws drop: dimethyl sulfide, or DMS for short. Now, you might be thinking, so what? It's just another molecule. What's the big deal? But here's the thing on Earth. DMS is only produced by living organisms. Specifically, it's generated by phytoplankton and other marine microorganisms. We've never found a non-biological process that produces this compound in any significant quantities. It's a biosignature, a smoking gun that points directly toward the presence of life. And Webb detected it in the atmosphere of K218b. Let me repeat that for emphasis. The James Webb Space Telescope has potentially detected a molecule on a distant exoplanet that, as far as we know, can only be produced by living things. The implications are absolutely staggering. If this detection is confirmed, and it's important to note that scientists are being appropriately cautious and conducting follow-up observations to make absolutely certain we could be looking at the first real evidence of life beyond Earth. Not microbial fossils on Mars, not mysterious signals from distant galaxies, but actual chemical proof that living organisms exist on another world, detected through their metabolic waste products floating in that planet's atmosphere. But let's pump the brakes for just a moment and talk about what makes this discovery so credible, because extraordinary claims require extraordinary evidence, and the scientific community isn't going to accept this lightly. The detection of DMS, while incredibly exciting, is currently at the edge of Webb's detection capabilities. The signal is there, but it's weak, right at the threshold of what the instruments can reliably measure. This is why scientists are being measured in their enthusiasm. They're excited, absolutely, but they're also professional skeptics who know that premature announcements can damage their credibility and mislead the public. What gives this discovery serious weight, however, is the totality of the evidence. It's not just about the DMS, it's about the entire package of what K218b represents. This is a planet that sits squarely in the habitable zone of its star, that Goldilocks region, where conditions are neither too hot nor too cold for liquid water to exist on the surface. Its host star, K218, is a red dwarf, smaller and cooler than our Sun, which means the habitable zone is much closer to the star than Earth is to the Sunday. K218b orbits its star once every 33 days, which seems rapid compared to Earth's 365-day year. But for a red dwarf system, this puts the planet right where you'd want it to be for potentially habitable conditions. The presence of methane and carbon dioxide together is also significant. On Earth, these gases coexist in our atmosphere largely because of biological processes. Plants consume CO2 and produce oxygen. Certain microorganisms produce methane. Without life constantly replenishing these gases, chemical reactions would cause them to react with each other and disappear from the atmosphere over geological timescales. The fact that Webb is seeing both gases in substantial quantities suggests something is actively maintaining their presence in K218b's atmosphere. And when you add the potential detection of DMS into that mix, you start to get a picture that's almost impossible to explain without invoking biology. There's another crucial piece of the puzzle that makes K218b such a compelling candidate for hosting life. Scientists believe it could be what's called a hycean world. This is a relatively new classification of exoplanet that's been proposed to describe worlds with hydrogen-rich atmospheres over global liquid water oceans. The name hycean is a combination of hydrogen and ocean, and these worlds represent a potentially vast new category of habitable planets that could be scattered throughout the galaxy. Here's why hycean worlds are so exciting. Traditional models of habitability have focused almost exclusively on rocky planets similar to Earth worlds with solid surfaces, relatively thin atmospheres, and the right temperature for liquid water. But hycean worlds expand the definition of habitability dramatically. These planets would be entirely covered by deep oceans, potentially hundreds of kilometers deep, with a thick hydrogen atmosphere above. The pressure at depth would be immense, and the environment would be utterly alien compared to anything we experience on Earth. But beneath those strange skies, in those dark, pressure-crushed depths, life could theoretically thrive. And here's the kicker. Hycean worlds could be far more common in the galaxy than Earth-like rocky planets. The universe seems to love making planets in that sub-Neptune size range. In fact, they're the most common type of exoplanet we've discovered so far. If even a fraction of these worlds are habitable hycean planets, the implications for life in the universe are profound. We could be living in a galaxy teeming with ocean worlds, each one potentially harboring vast ecosystems beneath their hydrogen skies. K218b fits the profile of a hycean world almost perfectly. Its size and mass suggest it has a substantial hydrogen atmosphere. The detection of water vapor in that atmosphere supports the hypothesis that a global ocean lies beneath, and the chemical signatures Webb is picking up are consistent with what you might expect from a world where biological processes are occurring in those alien seas. But let's talk about what 99.7% probability actually means in this context, because that number is being thrown around and it deserves careful examination. This isn't a number that scientists pulled out of thin air or assigned based on gut feeling. It's derived from statistical models that take into account everything we know about the planet's characteristics, its position in the habitable zone, the detected atmospheric composition, and the presence of those potential biosignatures. These models compare K218b to what we know about habitable conditions on Earth and other theoretical frameworks for life-supporting environments. The 99.7% figure represents the statistical confidence level that K218b possesses the necessary conditions for life as we understand it. Notice that careful phrasing, conditions for life, not definitely has life. There's a critical distinction here. This probability is telling us that based on everything we can measure and observe, this planet has nearly all the ingredients needed for life to exist and thrive. It's in the right zone around its star. It appears to have liquid water. Its atmosphere contains the right chemical compounds, and it just might have that telltale biosignature of DMS that would indicate living organisms are already there. But we need to be honest about the uncertainties too. We can't directly image the surface of K218b. We can't see oceans lapping against shores, or continents, or any kind of detailed geography. We're inferring all of this from spectroscopic data from the way light bends and filters through the planet's atmosphere during transits. It's an incredibly powerful technique, and one that's revolutionized exoplanet science, but it has limitations. There could be exotic chemical processes we don't understand that are producing these signatures without any biology involved. There could be false positives or instrumental artifacts that are making us see what we want to see. This is why the scientific process is so important, and why researchers are planning extensive follow-up observations. Webb will observe K218b again, probably multiple times, to confirm the DMS detection and search for additional biosignatures. Other telescopes will contribute their own data. Scientists will develop new models and refine existing ones. This isn't a one-and-done discovery announcement. It's the beginning of what could be a years-long investigation into this fascinating world. And even if the DMS detection doesn't hold up under further scrutiny, K218b remains an incredibly important target for study. It's one of the closest, potentially habitable exoplanets we've found, and it transits its star from our perspective, which makes it ideal for atmospheric characterization. Whether or not it harbors life, this planet is going to teach us enormous amounts about how worlds form, how atmospheres evolve, and what the boundaries of habitability really are. Let's zoom out for a moment and consider the bigger picture of exoplanet discovery and the search for life beyond Earth. When the first exoplanet orbiting a sun-like star was confirmed in 1995, just 51 Pegasi b, a hot Jupiter worlds away from anything habitable, it opened the floodgates. Scientists had theorized about planets around other stars for centuries, but actually finding them and confirming their existence was a monumental achievement. In the nearly 3 decades since that first discovery, we've identified more than 5,500 confirmed exoplanets, with thousands more candidates waiting for confirmation. The early discoveries were biased toward massive planets in close orbits to their stars. These so-called hot Jupiters were simply easier to detect with the technologies available at the time. But as our detection methods improved, we started finding smaller planets, cooler planets, and planets at greater orbital distances. We discovered the incredible diversity of planetary systems. Some stars have planets that orbit backwards compared to the star's rotation. Some have planets in such eccentric orbits that they swing from scorching heat to frozen wastelands every few months. We found planets orbiting binary star systems, giving real-world examples of Tatooine-like worlds with double sunsets. And gradually, inevitably, we started finding planets in the habitable zones of their stars. Rocky worlds, ocean worlds, planets that could, in theory, support life as we know it. The Kepler mission alone found dozens of potentially habitable planets, and TESS, its successor, has continued that legacy. But finding a potentially habitable planet and actually determining whether it hosts life are 2 very different challenges. That's where atmospheric characterization comes in, and that's where Webb is absolutely revolutionary. Previous telescopes could detect exoplanets and measure their basic properties, but they struggled to analyze atmospheric composition in detail, especially for smaller, Earth-sized worlds. Webb changes that equation completely. Its infrared capabilities, combined with its massive light-collecting area and incredibly stable pointing, allow it to detect molecular signatures that were simply impossible to see before. The detection of biosignatures in exoplanet atmospheres represents the holy grail of astrobiology. It's one thing to find a planet that could theoretically support life based on its temperature and the presence of liquid water. It's something else entirely to find chemical evidence that life is actually there, actively reshaping the planet's atmosphere through its metabolic processes. And that's exactly what we might be seeing with K218b. But let's dig deeper into why the specific combination of molecules Webb detected is so significant. The presence of methane and carbon dioxide together creates what scientists call a chemical disequilibrium, a state where gases that should react with each other and disappear are instead being continuously replenished. On Earth, our atmosphere is wildly out of chemical equilibrium. We have oxygen coexisting with methane, which shouldn't happen for long periods without some active process keeping both gases present. That active process, of course, is life. Photosynthetic organisms produce oxygen, while various microorganisms in wetlands, in the guts of animals, and in other environments produce methane. On K218b, the methane and CO2 combination tells a similar story. These gases should be reacting with each other, especially under the UV radiation from the host star. The fact that they're both present in detectable quantities suggests something is actively producing them. Now, there are some non-biological processes that can generate methane volcanic activity, for instance, or chemical reactions between rocks and water in the planet's interior. But when you combine that methane signal with the carbon dioxide, the water vapor, and potentially the DMS, you start running out of non-biological explanations that can account for everything we're seeing. The DMS detection, if confirmed, would be the most compelling piece of evidence because we have no known abiotic non-living processes that produce significant amounts of this molecule. On Earth, DMS is created primarily through the breakdown of dimethyl sulfoniopropanate, or DMSP, which is produced by marine phytoplankton. These microscopic organisms create DMSP as an osmotic regulator and cryoprotectant. And when the DMSP breaks down, it releases DMS into the water and eventually into the atmosphere. In fact, DMS from ocean phytoplankton is one of the main sources of sulfur in Earth's atmosphere over marine regions, and it plays an important role in cloud formation and climate regulation. If K2-18b truly is a hycean world with global oceans, and if those oceans harbor life similar to Earth's phytoplankton organisms that perform some kind of photosynthesis or chemosynthesis and produce DMS as a metabolic byproduct, then we'd expect to see exactly what Webb is potentially detecting. It's almost too perfect, which is one reason scientists are being so careful about confirming this finding. In science, when something seems too good to be true, it often warrants extra scrutiny. Let's consider what a hycean world like K2-18b might actually be like if you could somehow visit it. Picture this. You're approaching the planet in a spacecraft, and the first thing you notice is its size. It's noticeably larger than Earth, a super-Earth-sized world with a radius more than 2.5 times that of our home planet. As you get closer, you see that the planet is shrouded in a thick, hazy atmosphere. Unlike Earth's relatively thin blue envelope, K2-18b's atmosphere extends much farther from the surface, dominated by hydrogen and helium-like gases that Earth's gravity couldn't hold on to, but this more massive world retains with ease. The planet's color might be strange and otherworldly. The hydrogen-rich atmosphere could give it a pale, almost ghostly appearance, perhaps with hints of color from various atmospheric hazes and cloud layers. Methane in the atmosphere might create bands of color, similar to what we see on gas giants like Jupiter and Saturn, though less pronounced. You wouldn't see continents or land masses because, if the hycean hypothesis is correct, there aren't any. The entire planet is wrapped in a global ocean, dark and deep and completely alien. As you descend through the thick atmosphere, you'd experience increasing pressure and strange weather patterns. With a hydrogen atmosphere, the thermodynamics would be completely different from Earth. Cloud formation, precipitation, atmospheric circulation, all of it would operate on principles we're only beginning to understand theoretically. The boundary between atmosphere and ocean wouldn't be sharp like it is on Earth. Instead, there might be a gradual transition zone where the atmosphere becomes so dense and the pressure so high that it effectively liquefies, blending into the supercritical water ocean below. And then, finally, you'd reach the ocean itself. Not an ocean with a solid seabed a few kilometers down like Earth's oceans, but an abyss potentially hundreds of kilometers deep. The pressure at depth would be crushing, far exceeding anything found in Earth's deepest trenches. The darkness would be absolute. No sunlight could possibly penetrate these depths. And yet, if life exists here, it would have found ways to thrive in these extreme conditions. On Earth, we've discovered life in places we once thought were completely uninhabitable. Deep-sea hydrothermal vents, where superheated water rich in minerals spews from the ocean floor, support entire ecosystems based not on photosynthesis, but on chemosynthesis, the process of extracting energy from chemical reactions rather than sunlight. Organisms at these vents thrive in complete darkness, in water hot enough to melt lead, under crushing pressures. If life can exist there, then why not in the deep oceans of K2-18b? In fact, a hycean world might offer certain advantages for life. The thick hydrogen atmosphere would provide excellent insulation, keeping the ocean at a stable temperature regardless of the planet's distance from its star or variations in stellar output. The high pressure at depth could enable interesting chemistry that wouldn't be possible in Earth's relatively shallow oceans. And the sheer volume of liquid water, potentially orders of magnitude more than Earth contains, would provide an enormous environment for life to explore and diversify. But there's a darker side to consider as well. K2-18b orbits a red dwarf star, and red dwarfs present their own unique challenges for habitability. These small, cool stars are the most common type in the galaxy, which is great news for planet hunters because it means there are lots of potential targets to study. But red dwarfs are also prone to violent stellar flares, massive eruptions that can blast nearby planets with intense radiation and charged particles. For a planet as close to its star as K218b is, these flares could be a serious problem. Earth's magnetic field protects us from the worst of the sun's radiation and solar wind. But we don't know if K218b has a magnetic field or how strong it might be. If the planet lacks significant magnetic protection, stellar flares could strip away atmospheric gases over time, potentially even affecting the ocean below. However, the planet's thick atmosphere might provide its own form of shielding, absorbing and dissipating the flare energy before it reaches the ocean surface. There's also the question of tidal locking. Planets in close orbits around their stars often become tidally locked, meaning the same hemisphere always faces the star, just as the moon always shows the same face to Earth. If K218b is tidally locked, one side would be in perpetual daylight, while the other experiences eternal night. This could create extreme temperature gradients and bizarre weather patterns, with heat from the day side driving massive atmospheric circulation patterns that redistribute energy to the night side. However, a global ocean actually helps mitigate this problem. Water is excellent at storing and transporting heat. Ocean currents would circulate warm water from the day side to the night side, preventing one hemisphere from freezing while the other boils. The thick atmosphere would also help redistribute heat through powerful wind patterns. So even if K218b is tidally locked, it might still maintain relatively stable, potentially habitable conditions across much of the planet. Now, let's address the elephant in the room, the question everyone wants answered. If there really is life on K218b, what might it be like? The honest answer is that we have absolutely no idea beyond the most general speculation. Life on Earth exhibits staggering diversity, from bacteria that can survive in nuclear reactor cooling ponds to complex multicellular organisms like whales and redwood trees. But all of Earth's life shares common features: DNA as a genetic material, proteins built from the same 20 amino acids, cells with lipid membranes. We're all related, all descended from a common ancestor that lived billions of years ago. Life on K218b, if it exists, would have arisen completely independently. It might use entirely different chemistry. Instead of DNA and RNA, it might use different molecules for information, storage, and transfer. Instead of proteins, it might build its cellular machinery from completely different polymers. Its cells might be structured in ways we can't even imagine. The only thing we can say with any confidence is that if it's producing DMS through processes similar to Earth's phytoplankton, it's probably microscopic and ocean-dwelling. But let your imagination run wild for a moment. What if K218b's oceans are filled with vast blooms of alien microorganisms, trillions upon trillions of them, carrying out photosynthesis using the dim light that filters through the thick atmosphere? What if there are more complex organisms that feed on these microbes, creating entire food webs in those alien seas? Could there be creatures analogous to fish or jellyfish, or something completely beyond our biological reference frame? Could there be ecosystems clustered around hydrothermal vents in the deep ocean floor? If K218b has active geology? The possibilities are intoxicating, but we need to stay grounded in what we can actually observe and test. Right now, we potentially have evidence for one thing: a molecule that on Earth is produced by very simple marine organisms. That's remarkable enough on its own. If we can confirm that DMS is really there, and that it's being produced biologically, we will have answered one of humanity's oldest and most profound questions. Are we alone? And the answer will be a resounding no. But even that wouldn't be the end of the story. It would just be the beginning. Confirming life on K218b would immediately spawn 1,000 new questions. How did that life originate? How long has it been there? Did it arise independently? Or could there be some mechanism for panspermia, the spreading of life between star systems that we don't yet understand? Is it based on the same fundamental chemistry as Earth life, or something entirely different? Has it evolved beyond simple microorganisms? Or is the planet's ocean filled with nothing but bacterial equivalent organisms? These questions would drive decades, possibly centuries of follow-up research. Scientists would dedicate their careers to studying K218b from afar, squeezing every possible bit of information from spectroscopic observations. Engineers would start designing concepts for interstellar probes that could make the journey, even if such a mission wouldn't arrive for thousands of years. The discovery would fundamentally reshape our understanding of biology, chemistry, and our place in the cosmos. It's worth considering the statistical implications of finding life on literally one of the first potentially habitable exoplanets we've examined in detail. K2-18b isn't particularly special in cosmic terms. It's not the closest exoplanet to Earth. It's not in the most perfect orbital position. It's not the most Earth-like world we've discovered. It's just one of the first planets that the James Webb Space Telescope has been able to study with enough precision to detect potential biosignatures. And if life is there, what does that tell us about how common life is in the universe? If we find life on one of the first few planets we examine closely, it would suggest that life isn't rare at all. It would imply that the universe is absolutely teeming with living worlds, that perhaps the majority of planets in habitable zones around their stars develop some form of life. The numbers become staggering when you consider that there are an estimated 100 billion stars in the Milky Way galaxy alone, and at least as many planets. If even 1% of those planets harbor life, we're talking about 1 billion living worlds in our galaxy. And there are hundreds of billions of galaxies in the observable universe. Alternatively, we might be witnessing an incredible stroke of luck. Maybe K2-18b is one of the very few worlds where life has arisen, and we just happen to point our best telescope at it. Maybe life is rare, and it requires such a specific set of conditions and fortunate coincidences that it only emerges on a tiny fraction of potentially habitable worlds. In that case, finding life on K2-18b would be even more remarkable, a cosmic lottery win of incomprehensible odds. There's also a middle possibility, that simple, microbial life is relatively common in the universe, but complex, multicellular life is rare. On Earth, life appeared quite quickly after the planet cooled down enough to support it, emerging within a few 100 million years of Earth's formation. But it took billions of years more for complex, multicellular organisms to evolve. For most of Earth's history, the planet was dominated by single-celled organisms. Perhaps the universe is filled with planets like K2-18b worlds with oceans full of microbial life that never develops beyond that stage. Intelligence, technology, civilization, these might be the true rarities, even if simple life is everywhere. The scientific community is already debating what finding life on K2-18b would mean for the Drake equation, the famous formula that attempts to estimate the number of communicative civilizations in our galaxy. The equation considers factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, the fraction of those planets that develop life, and so on. Confirming life on K2-18b would give us actual data for one of those variables, the fraction of habitable planets that develop life, which would dramatically improve our ability to estimate how alone or how companioned we are in the universe. But let's return to the immediate present and the actual science being done right now. The James Webb Space Telescope's observation of K2-18b wasn't a simple snapshot. It involved multiple transits, with Webb carefully measuring how the star's light changed as it filtered through different parts of the planet's atmosphere. The data reduction and analysis process is incredibly complex, requiring sophisticated computer models to separate the tiny atmospheric signals from the much brighter background of the star itself. The scientists working on this data aren't just looking for biosignatures. They're also characterizing the planet's temperature structure, looking for evidence of clouds and hazes, trying to determine the planet's atmospheric pressure profile, and searching for additional molecules that might be present in trace amounts. Every piece of information helps build a more complete picture of what this world is actually like. One of the challenges in interpreting the data is that we don't have perfect templates for what a hycean world spectrum should look like. We can't just compare K2-18b to Earth or Venus or any planet in our solar system because none of them are good analogs. Scientists have to rely on theoretical models of hycean atmospheres, which themselves are based on our understanding of physics and chemistry extrapolated to exotic conditions. These models make predictions about what molecules should be present and in what abundances, but they could be missing important processes or chemistry that we haven't thought of yet. This is where the scientific method really shines. The initial Webb observations suggested the presence of DMS, which was unexpected and exciting. Now, scientists will develop new models that try to explain this detection. Some models will propose biological sources. Others will try to find abiotic mechanisms that could produce the same signal. Each model makes testable predictions about what else should be present in the atmosphere, or how the DMS abundance should vary, or what other signals we should see. Then, follow-up observations with Webb and eventually other telescopes will test these predictions, allowing scientists to rule out incorrect models and refine the correct ones. This process takes time, often years, which is frustrating for those of us eagerly awaiting confirmation. But it's the only way to be sure we're getting the science right. Premature announcements can lead to embarrassment and eroded public trust in science. Remember the excitement in 2020 when scientists announced the detection of phosphine in Venus's atmosphere? Phosphine, like DMS, is a potential biosignature, a molecule that on Earth is primarily produced by living organisms. The initial detection sparked enormous excitement about the possibility of life in Venus's clouds. But subsequent analysis raised questions about the detection, and other teams couldn't confirm the finding using different data or different analysis methods. The Venus phosphine story isn't closed, but it serves as a cautionary tale about the importance of verification and the dangers of over-interpreting preliminary data. The scientists studying K218b are acutely aware of this history. They're being appropriately cautious, emphasizing that the DMS detection is tentative and requires confirmation. They're also being careful to present the full range of possibilities. Yes, the detection could indicate life, but it could also be a false positive, an instrumental artifact, or the result of some exotic chemistry we don't yet understand. This kind of scientific humility is essential, even when it dampens the excitement a bit. That said, the totality of evidence for K218b is genuinely compelling. This isn't like the Venus phosphine situation where there was one surprising detection and everything else was ambiguous. With K218b, we have a planet in the habitable zone, with water vapor, with methane and carbon dioxide in chemical disequilibrium, and potentially with DMS. Each piece of evidence reinforces the others, building a coherent picture of a world that could be habitable and possibly inhabited. The 99.7% probability figure, while attention-grabbing, should be understood in its proper context. It's not saying there's a 99.7% chance that life currently exists on K218b. Rather, it's saying that based on our current understanding and the available data, there's a 99.7% probability that the planet possesses the necessary conditions for life to exist. It's a subtle but important distinction. The planet could have all the right conditions and still be lifeless, just as you could have a perfectly good field but no crops growing in it. Nevertheless, the fact that we can even assign such a high probability to another world's habitability is itself revolutionary. Just a generation ago, we didn't know if planets around other stars even existed. Now we're not only finding them by the thousands, but we're also characterizing their atmospheres and assessing their potential for hosting life. The pace of progress has been breathtaking. Looking ahead, what comes next for K218b research? The immediate priority is confirming the DMS detection with additional Webb observations. The telescope will observe more transits, gathering more data and improving the signal-to-noise ratio. Scientists will also use different instrument modes and observation strategies to see if they can detect DMS through multiple independent methods, a crucial step in verification. Beyond DMS, researchers will be looking for other potential biosignatures. Oxygen would be significant, though it can be produced by non-biological processes. Ozone would be even more interesting. Methyl chloride, another molecule primarily produced by life on Earth, would be another piece of evidence. The detection of multiple independent biosignatures would dramatically strengthen the case for life. Scientists will also be refining their understanding of K218b's basic properties. Better measurements of the planet's mass and radius will help constrain its internal structure, how much of it is ocean versus rocky core versus atmosphere. Understanding the thermal structure of the atmosphere will help determine whether the surface conditions are truly compatible with life as we know it. Detecting weather patterns or atmospheric dynamics would provide insights into the planet's climate system. Other telescopes will contribute to this effort as well. The European Extremely Large Telescope, currently under construction, will have capabilities complementary to Webb's. Future space missions, like the Habitable Worlds Observatory, still in the planning stages, are being designed specifically to characterize potentially habitable exoplanets. K2-18b will be a prime target for all of these instruments. In the longer term, K2-18b could become the focus of even more ambitious proposals. Some scientists have suggested that a dedicated space telescope designed to study just this one planet in extreme detail could answer many of the outstanding questions. Others have proposed more exotic ideas, like using the sun as a gravitational lens to create ultra-high-resolution images of distant exoplanets. Though such a mission would require sending a spacecraft far beyond Pluto's orbit and would take decades to implement. And then there's the wildest idea of all, actually sending a probe to K2-18b. With current technology, such a mission is pure science fiction. The journey would take millions of years, and we have no way to build a probe that could survive that long or transmit data back across such vast distances. But if we could somehow develop revolutionary propulsion technology that could make the journey in thousands of years instead of millions, or even in centuries, K2-18b would be at the top of the list for destinations. Imagine the day when a probe actually arrives at K2-18b, thousands of years from now. It begins its orbital insertion, using its instruments to map the planet in unprecedented detail. It deploys smaller probes that descend through that thick hydrogen atmosphere, taking measurements and samples every kilometer of the way. And finally, one of those probes splashes down in that alien ocean, the first human-made object to touch the surface of another potentially living world beyond Earth. The probe's sensors activate, sampling the water, analyzing its chemistry, searching for the microorganisms that might be creating those atmospheric biosignatures detected so long ago by the James Webb Space Telescope. And if it finds them, if it captures images of alien cells, alien biology, alien life, the data packet it sends back across the cosmic void would represent the culmination of humanity's greatest quest. But we don't have to wait thousands of years to appreciate what we're learning right now. The James Webb Space Telescope's observations of K2-18b, regardless of whether they ultimately confirm the presence of life, represent a watershed moment in astronomy. We are living in the era when humanity first gained the capability to search for life on other worlds, not through speculation or wishful thinking, but through rigorous, quantitative analysis of actual data from real planets. The 99.7% probability that K2-18b could harbor life isn't just a number. It's a reflection of how far we've come, how much we've learned, and how close we might be to answering the ultimate question. Whether we're alone in the universe is no longer just a philosophical debate, it's becoming an empirical question that science can actually address. And K2-18b might just be the world that provides the answer. The universe has been keeping this secret for billions of years. But now, with instruments like the James Webb Space Telescope and the brilliant minds working to interpret its data, we're finally developing the tools to uncover the truth. K2-18b shines in the constellation Leo, 124 light-years away, its mysteries waiting to be revealed. And here on Earth, we're watching, measuring, analyzing, inching, ever closer to one of the most profound discoveries in human history. Whatever we ultimately learn about K2-18b, one thing is certain: we're living through a golden age of exoplanet science, and the discoveries we're making today will reshape humanity's understanding of our place in the cosmos for generations to come. The search for life beyond Earth is no longer science fiction. It's science fact happening right now, one spectroscopic observation at a time. And K2-18b, with its 99.7% chance of having the right conditions for life, might just be the world that changes everything.